In this video, we're going to build on what we've been learning about Newton's laws and forces, and we're going to add some quantitative aspects to this so we can start to deal with quantitatively analyzing certain situations. So, just to recap what we've been doing, we've covered Newton's first and second law. Newton's first law was an object in motion stays in motion. An object at rest stays at rest unless some external force acts on it. So this is essentially sort of setting the tone for what forces do, right? They cause accelerations. They change the motion of an object from uniform motion, constant speed in a straight line, and either cause it to sort of turn, changing its velocity, or speed up or slow down in some way. And Newton's second law is probably the most important equation in the course. F net is equal to ma. And this is a vector equation. So we looked at how to identify forces and look at all the forces involved acting on our object. We can add those up, and then that's going to cause some acceleration on that object. So that was Newton's second law. We also started discussing equilibrium, right? And that was the case where the net forces, all the forces added together in a way that balanced, so the net force was zero. Or equivalently, the object had no acceleration. And there were two kinds: static equilibrium for things that are staying still, and dynamic equilibrium for something that was moving, but moving with a constant velocity or zero acceleration. And then we started to outline this sort of problem-solving strategy that's gone through in the text, where the first thing we do, and we're trying to analyze a situation in dynamics where all forces are involved in that, is identify the forces acting on the object we're trying to analyze. So we identify all the forces. After that, we draw some free body diagram. We particle model. It might have various forces acting on it. Sorry about that. Gravity. Maybe it's got a rope pulling on it with some tension or what have you. But draw a free body diagram to give us a representation of the forces that would be acting on our object. Then we define some coordinate system, some x direction and some y direction. That is going to allow us to apply Newton's second law, this equation here, in that coordinate system. Because again, this is a vector equation. So we're going to have to break these vectors into components so we can add them together. And today what we're going to do is we're going to start to, this is as far as we've gotten, we're going to start to look at the different forces quantitatively and say, okay, we know there's a force due to gravity. How can we calculate what that force is? So to start, what is gravity? Well, gravity is an attractive force between any two objects with mass, right? So you have some mass, objects in your room have some mass. There is an attractive force between those objects and all objects with mass. And that force is proportional to the amount of mass in those two objects. And it's inversely proportional to the square of the distance between those two objects. This was sort of one of the big things that Newton discovered. Is he realized that the force of gravity is described by this equation. This is Newton's universal law of gravitation. Essentially, the magnitude of the force between any two masses is going to be this constant g here, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the first object, times the mass of the second object, divided by the r, the distance between those two objects squared. So you have two really big masses, that's going to be a strong force. If they're really close together, it's going to be a stronger force. The further apart they are, the weaker the force is. And that's how it works. One of the things we can notice if we look carefully at this, is the magnitude here. This g, this gravitational constant g, is an extremely small number, right? It's 10 to the minus 11 Newton meters squared per kilogram squared. So if we take, two objects, let's say let's round up and say a human's, 100 kilograms. That's a pretty, it's 220 pounds. Um, so let's say we have a mass one around 100 kilograms, mass two, we'll say the same thing, 100 kilograms, which is equal to 10 to the 2 or 10 to the 2 kilograms. Um, and let's say, well, let's say we're in the same room, we're about a meter apart. So we're 1 meter apart. This would mean the magnitude of the force of gravity between those two objects, you and another person in the room, is going to be G m1 times m2 over r squared. Well, what is this going to be, right? Now, we don't even have to keep the details. If we were looking for like an order of magnitude, this is around, well, let's keep the details, might as well. 6.7 times 10 to the minus 11 is the gravitational constant, times 10 to the 2 for the mass of the first one, times 10 to the 2 for the mass of the second one, all divided by 1 squared, which is that. If we're looking at this, this is 10 to the 2 times 10 to the 2 is 10 to the 4. So this is going to be 6.67 times 10 to the negative 11 plus 2 plus 2. This is 6.67 times 10 to the minus 7, right? So this is less than a micronewton. This is an extremely small force acting on you. And this is why we generally ignore gravity between two objects on the surface of the Earth. We never really concerned with the gravitational attraction of you and something else in the room because these forces are just extremely small. Now, what does matter is Earth. Earth has a huge mass and it's really quite large. So that's generally, when we're speaking of gravity, that's the force that we're concerned with in most cases. The attractive force between something near Earth's surface and the Earth, because that's the only force of gravity that's really significant. And when we do that, we can make some approximations, right? That force is again, going to be G times the mass of the object times the mass of the Earth divided by the distance between the object and the Earth squared. Now, if we look at these things, well, the mass of the Earth is huge, right? You can look it up in the front of your textbook. G is really small, and the radius, the distance between the Earth and that object, is essentially just the radius of the Earth. I mean, if you look at the radius of the Earth and you add, even 100 meters because you're at the top of a skyscraper, it's really approximately the same number as the radius of the Earth. So we can take those numbers that are going to be roughly the same for anything near Earth's surface. So that G, the mass of the Earth, and the radius of the Earth squared, and sort of factor that out, and then times the mass of the object near the surface of the Earth that we're concerned with. And we can just, since these are going to be the same for essentially all things near the surface of the Earth, we can define a new constant, this lowercase g here, and multiply that times the mass of the object we're concerned with. So that means is if we're looking for the force of gravity for some object near the surface of the Earth, the magnitude of that force is just going to be, well, the mass of that object times this little g. And that little g is, typically accepted as 9.8 newtons per kilogram, or equivalently meters squared, or meters per second squared. And this is how we can now model the force due to gravity on Earth, right? If we have some object near the surface of the Earth, we know that the magnitude of the force of gravity is going to be equal to this, and it's going to be pointed, because that force of gravity is, between those two objects, it's going to be pointed straight down towards the center of the Earth. So this is how we can quantitatively put some numbers into what the magnitude of the force of gravity is on Earth. And we generally don't consider, or the forces of gravity to other objects in that is too small. It's insignificant. It's not going to be really have a measurable effect on the things, anything we're concerned with, right? One thing I want to bring up that is kind of it's a crucial sort of thing you should be aware of, is the difference between mass and weight. All right, this is another one of those things where the language we use in physics is slightly different than the language we might use in everyday. And these masses in our force due to gravity uh, are masses. They're not weight. The difference being mass is an intrinsic property of an object, right? So if you take a medicine ball or some big object, you can feel it getting pulled towards the earth. You can feel the force of gravity pulling it down. But if you were to try and move that and accelerate it, it's going to have some resistance to that. That's the inertial mass. But that mass doesn't change. If you were to get on a spaceship, go into interstellar space, away from all the planets, and you were to try to move that mass, it would be just as hard for you to move it. It has the same amount of stuff in it. It's a property of that object. It has nothing to do with how strong the force of gravity is at that moment. So mass is a property of the object, whereas weight is sort of a measurement. It's a measurement of the force due to gravity. If we're on Earth and we're standing still, that weight is equal to the force of gravity. And we just went over how to calculate that. It's going to be equal to that mg. One of the ways you can think about the difference between the two is if you were to take two known masses and put it on a balance, presumably they're both on Earth, and that would be comparing the masses of the two objects. Whereas if we were to measure it on a spring scale, so the way that a spring scale would work is you put an object on top of something with calibrated springs. These springs have a known strength. The force of gravity pushes this object downwards. The springs start to compress and push it back. Eventually, they hit equilibrium. The spring force balances this force due to gravity, and you would measure how far these springs compressed in that, and it turns out from that you could determine the magnitude of the force of the spring, and since it's in equilibrium, that would have to equal the force due to gravity, and you would have made a measurement of the force due to gravity, and we would call that the weight. There are, if you go through the text, they spend a bit of time talking about this in more detail. If this whole setup is accelerating, though, you're no longer in equilibrium, so there's an apparent weight. But rather than go off on this tangent, because I want to get through a quick example, the idea is mass is an intrinsic property of the object. It's going to be the same whether you're in space, whether you're on Earth, whether you're on Mars. Whereas weight relates to the force of gravity. So you have a weight on the surface of the Earth equal to mg if you're in equilibrium. Whereas if you were in interstellar space and there were no mass, no planets or anything around you, your weight would be zero. You'd be weightless. All right. So let's look at an example. Let's say we have some crate, some box, some object we're trying to lower. It weighs 1,200 kilograms, and we're using a cable that we've bought that has some maximum tension of 11,000 newtons. So with this cable spec'd at, keep it under 11,000 newtons. This cable's strong enough, it won't break. Above that, there's a chance it might break. You can't sue us. We've given you your warning. And what you're doing is you're lowering this box downwards at 0.15 meters per second at a constant speed. Question is, will the cable snap? Is that safe, right? So how do we answer this? How do we answer this question? Well, the real question we're trying to sort out is, what is the tension in that cable, and is it greater than, is it greater than our maximum safe tension, right? So to figure this out, we're going to go through our process of problem solving. The first thing we do, we need to ID forces, right? So we pick the object we want to describe, and in this case, we're looking at that crate, right? And we're going to look at all the forces acting on it, and we need to identify those forces. So we went through how to do this in previous videos. Circle the object, right? And identify everything that breaks through that circle. And the only thing touching or touching our object is that rope, which is our force of tension. So we've identified all our contact forces. Now, the next thing we do is we look at our long-range forces, and we're on Earth. Long-range force is gravity. Right, so we've identified the two forces that are going to be involved in this problem. The next step is, well, draw a free body diagram, right? So we can have some model of how we're doing this. So we are using the particle model, so that's our crate. We know tension is always in the direction of the rope. So tension is going to be straight up. We have the force of tension going straight down. And gravity, as we just discussed, is always pointed straight down towards the center of the Earth, and it's gravity. The next step we do is our next step in the process is pick coordinates, a coordinate system. In this case, it's a one-dimensional problem. Everything's going up and down, so we'll call up the y direction. You know, just for completeness, we'll call left and right x, but nothing's going on in the left or right direction. So we're going to focus just on y. And then the last step is apply Newton's second law, F net equals ma. And to do that, again, this is a vector equation, so we're going to do this in coordinates. Now, we're looking at a one-dimensional problem, so we're only going to look at the y component because that's the only direction we have. And we have F net is equal to ma in the y direction. And we want to kind of think about these two sides of the equation separately. The left side is everything we know about the forces. We know there's two forces, tension and gravity. So we have tension in the positive direction, so we have the magnitude of tension going up, and we have gravity in the downward direction. So negative whatever the magnitude of that force of gravity is. On the right-hand side of the equation, we have mass times the acceleration. We know something about the acceleration, right? In the problem, we've described how that box is moving, and we've spent a couple weeks going through kinematics and what that means. If I'm moving in a straight line at a constant velocity, my acceleration is zero. So I am in equilibrium. So the left-hand side of the equation is just zero. So I have tension minus gravity is equal to zero. Now we can take what we learned today, and we know that the magnitude of the force of gravity is equal to mass times that little g. So this equation, when we plug that in, is T minus mg is equal to zero. And doing some algebra, T is equal to mg in this case. We know the mass, that's 1,200 kilograms. We know g, I'll put this in parentheses just to keep them separate. We know g is 9.8 newtons per kilogram. So when we go through this calculation, we end up with 11,760 newtons, right? The kilograms cancel. We have the units right. So we've solved for what the tension in our rope is. And this tension is greater than 1,100 newtons. So there's a good chance that this rope will snap. This is sort of an unsafe situation to be in. You don't want to use this cable for that thing. But again, hopefully this is a nice first example through how this problem solving strategy works. We'll do many more in our synchronous sessions, and hopefully we get really comfortable with this process of identifying the forces, drawing our free body diagram, picking a coordinate system, and then just applying Newton's laws by breaking all those forces into components. If you have any questions, email me, and I will see you in our synchronous sessions.